if 3x minus 5 is less than or equal to f of x, which is less than or equal to x squared minus 3x plus 4, for x greater than or equal to 1, find the limit as x approaches 3 of f of x. Now here we don't have an equation that defines f of x, but we know that it is squeezed or sandwiched in between these two other functions, at least for x greater than or equal to 1. But if we're looking at the limit as x approaches 3, then that's definitely greater than or equal to 1. That's greater than 1, so we know that in a whole neighborhood around this, the function is squeezed between these other functions. So if both of these functions have the same limit as x approaches 3, then the limit of f of x is going to have to be equal to that because it is sandwiched between them. So let's evaluate these individual limits. Let's look at the limit as x approaches 3 of 3x minus 5. Now that is a polynomial function, so we can use direct substitution. So it's going to be 3 times 3 minus 5, and 9 minus 5 is 4. Let's look at the other limit and see if it is also equal to 4. So we've got x squared minus 3x plus 4. That is also a polynomial, so we can use direct substitution. 3 squared minus 3 times 3 plus 4 is going to be 9 minus 9 plus 4. Of course, the 9's cancel, and we're left with 4. And so, because both of these functions have a limit that exists, and those limits are equal to each other, and f of x is sandwiched or squeezed in between those, that means that the squeeze theorem tells us that the limit as x approaches 3 of this function, f of x, must also equal 4. We don't know what f of x is, but we know that that limit has to equal 4. Let me show you graphs of these other two functions so you can have an idea of what's going on here. All right, this is from a graphing calculator. This parabola is the larger function, x squared minus 3x plus 4. And then the linear function is the smaller function, 3x minus 5. And remember, we're looking at what happens as x approaches 3, which is right here. That's going to be 3. And we know that so long as x is greater than or equal to 1, our function f of x is squeezed in between those. So greater than 1, we don't really know what's going on. It might be oscillating, it might not. And then on the other side, kind of the same thing is happening. No idea what the function looks like. It's just between those two. And less than 1, it may or may not be between those two. It doesn't really matter. But this is an example of what our function could look like. And remember, we only care about what's happening near 3. So we only care about what's happening in here. And because in this neighborhood, our function f of f is sandwiched between these two, and because these two come together and have the same limit here, they're effectively squeezing f of x in between them and causing it to also have the same limit of 4. If you look at the scale on the y-axis, this is 5, 10, 15, 20. 4 is just underneath it, and you can see by the graph that limit is equal to 4. So having the graph, I think, gives a little bit of a visual representation of why this actually works and what's actually going on. But we can solve the problem without the graph. We don't need the graph for the squeeze theorem. I'm just including it because I think it might help you comprehend this, what's going on, a little bit better.